Good morning, everyone. Can you hear me well? Very good. So thanks to the organizer for inviting me to give these lectures. Now, it's not easy to give the class, the lecture I'm going to give, which is basically Amplitudes for Phenomenology, because I know that many of you are actually not so interested in phenomenology, but said many of you. But so I will start by telling you why it is important to do amplitude for phenomenology and what are the challenges, because it's a slightly different game than studying the structure of scattering amplitude. Of course, a huge amount of cross-contaminations, and we really like to understand structures and use these structures to do, let's say, LHC predictions, but the game is slightly different. Now, why do we need amplitude to do phenomenology? Well, as you all know, we have the LHC, that's all the Higgs, and basically nothing else, okay? This you can ask Nima, is challenging our understanding of how we think about fundamental physics, but it puts us also in a quite peculiar situation as far as what to do next goes, okay? So what do I mean nothing else? Well, if you open a random talk by an experimentalist that summarizes the status of LHC searches right now, they're going to tell you that they search for SUSY, they search for scales at which may, let's say the Higgs score at the top make a compositeness. They look for extra dimension, whatever you want, okay? And they found that they can exclude many of these models. Of course, there are always caveats. It's always possible to cook up something that is very easy to hide at colliders. But roughly speaking, they tell you that they don't see any of these things in the region between 1 TeV to 10 TeV. And then they lose steam because they don't have enough energy, okay? So they seem to suggest that if there is something that LHC can see, it's slightly at higher scale than what we may have expected or hoped before, okay? Now, how can we do this? Well, again, as I said, so LHC is running out of steam, so it will accumulate a huge amount of data, but it will not go up in energy significantly, okay? So if there is a new resonance which is not accessible, we will not see it for the foreseeable future, okay? But we all know that we can use, that basically nature of LHC is described by quantum field theorists. And if we have very heavy degrees of freedom, they can be seen at low scales, even if we don't have direct access to them through the framework of EFTs, if you want, okay? So what do I mean by that? No. So just imagine that you have a new physics at the scale here. Let's say here is our LHC exclusion limits, and we want to do experiments to smash protons at around the delta weak scale, okay? Now, we cannot produce these things directly. But if you think about what happens in real life, then these particles decouple from your spectrum. You can integrate them out in a path integral. Basically, they don't introduce non-analyticities. It's relatively straightforward to do this. But they leave an imprint in the low energy world. And they leave an imprint which is a power correction. So if you have or not have something up there, down here, what you see is something that goes like a scale at which you do your experiment times a scale of new physics raised to some power. And the power depends by the kind of operators that is in the UV theory. Now, in the standard model, there is one operator of dimension 5, which is the one that gives, let's say, Majorana mass to neutrinos, flavor-violating. But this points to a scale which is very, very large, so these effects are tiny. So effectively, when we talk about what is the effect of heavy degrees of freedom at LHC, we basically talk about dimension 6 operators that leave quadratic imprint to your low energy physics. Now, if we have 1 to 10 TeV and we do experiments at 100 GeV, this tells you that in order to see this thing, it is possible to see these things here, but in order to see them, you need to control what goes on here at least a few percent level. Okay. And that is a key. So in order to profit from what the LHC is producing, we need to control theory. We are no longer in the game of finding new references. I mean, it can still happen, of course. I'm not saying it's impossible, but this is becoming more and more important. Now, this is not easy because the LHC is a complicated machine. It smashes protons. And we do not know how to compute stuff starting from strongly coupled quantum field theories. Okay? So what do we do? Well, again, we use similar ideas of factorization, basically when you have degrees of freedom which are widely separated, to write down predictions that we can compute from first principles in terms of quark and gluons rather than protons. And there's a small price that we have to pay. We have to hide somewhere the fact that actually we are scattering protons and not partons. Now, this is a little bit hand-wavy, but it can be put in a somewhat rigorous form. Now, it can be put in a quite seriously rigorous form in case of deep inelastic scattering. So just imagine that you scatter basically proton of electrons through a virtual photon. Crucially here, since these are we have high energy, so we can imagine this is light-like. So this is basically space-like. So if you are at very, very high energy, so this is very, very large in absolute value, then you can basically factorize the development operator product expansion to factorize this object here and write this. Roughly speaking, that your cross-section, roughly speaking, is a convolution of a part that you don't control, I'll tell you in a second what it is, times interaction of quark and gluons. So this you can split it out in something like that. So you have your protons that emits, let's say, a quark. The quark emits, interact with the virtual photon and do something like that. Now this is an object that encodes our ignorance on the proton and basically tell us how likely, roughly speaking, this is all hand wave, yeah? How likely is to find a quark in a proton, okay? Now, what does this object depend on? Well, it depends on the longitudinal fraction because this object is very, very boosted. So the only non-trivial degrees of freedom in the first approximation are longitudinal. So this object here will depend on the fraction of momentum that this quark comes down, and it can be interpreted, roughly speaking, as a probability. Now, this whole hand-wavy, life is more complicated, so this can be done properly with an OPE and whatever. So this becomes a matrix element of an operator, and as usual in QFT, this gets renormalized. So this basically depends, stat dependency on scales. That basically tells you the scale at which you are probing the proton, and every time becomes more complicated, but this picture stays. So basically the idea is the following. So the physical picture that underlies this is that you have an extremely high energy scattering that you're interested in. So let's say you have a scattering at the scale of hundreds of GeV, and you have proton physics at the scale of 1 GeV, where the proton confines. Okay, so these scales are so separate that basically the proton doesn't not have time to react to this high energy process. So the typical scale, the typical time scale of this is much slower than the typical scale that you're interested in. So what let's say what this object is seeing, what your hard probe is seeing, is not complicated infrared dynamics, but it's seeing an instantaneous snapshot of the proton. Okay, so that is roughly speaking how it works. Again, it can be made precise in this case. Interestingly enough, it cannot be made very precise in what we care about, which is hadron collisions. So hadron collisions seem very, very simple, very similar, sorry. Only we have two protons. And just imagine I want to produce a Higgs. I can extract a gluon from here. Okay, and I produce my Higgs. Okay, the picture seems very similar. And the picture that I told you stays the same, right? If I have to produce a Higgs here, I'm doing scattering at least at 100 GeV scale. And then the protons are basically frozen. However, there's a crucial difference between up there and here. So here, the process is time-like. And I cannot really define an operator product expansion. So I cannot really prove on rigorous ground factorization. So what do? Well, in this case, and all our predictions, let's see all of them, every single one of them, are based on the hope that that picture generalized down here. Okay. Now, of course, it's not just wishful thinking. We have wishful thinking, so people actually studied a lot this, and perhaps we will hear about later on in the week. It's in simple cases, like for example, Higgs production or Dralian production, so there's not a lot of color going around, you can prove that things should actually work well. When you start having a lot of color going around, you may have problems. And the typical problem that you may have is that long before the interaction, the two projectiles can actually exchange long distance softish, not really softish, but let's say Coulomb modes that can spoil factorization. Until a couple of weeks ago, this was thought to be a real problem. So starting from a significantly higher order. Now, situation changed a little bit. We can discuss if you're interested. So it seems that this is no longer such a problem. This may not be a problem after all. But I want you just to, in this introduction, I just want to tell you that everything that we do is based on this picture. And this picture may have problems when we go precise enough. OK? Now, let me write this in a little bit more formal way. So we have that the quantity that we want to compute, so basically our general observable, a cross-section, whatever observable you like, can be written as an integral over this object which describes the structure of the proton, called pattern distribution functions. That depends on a scale. And let's say I do this, I do the Higgs, so this gluon, gluon. And longitudinal fractions times, times the cross-section for the hard process, which is written in terms of this objective. And this will depend in general on the normalization scale and on this scale here that basically tell us how much radiation we want to put, how much stuff we want to put into the proton, and how much stuff we want to actually compute. This is typical scale that you have every time you have a factorization. And it's called factorization scale. Okay. Now, this is not exact. So as usual, when you have factorization in QFT, you get very nice logarithmic behavior, but this is corrected by our corrections. So this is true up to object that scales like the scale of a process. Sorry, the scale of the process over the QCD confinement scale. So let's say the strong QCD scale or the 1 GeV over the scale of the process to some power. Okay. And as you can imagine, if we want to go to 1%, okay, and if QCD scale is 1 GeV, okay, then we're already in trouble, in deep trouble. So if this is true, we cannot do it. Okay, so we can compute whatever amplitude we like, and 92 loop scattering amplitude for 62 million legs. It's completely pointless. Okay. So there's been a lot, as you can imagine, because of this, there's been a lot of progress in trying to understand these objects. And there's some hope that for many interesting observables, actually this scales quadratically. So this becomes a non-issue. I will not have time to discuss this, but I'm very happy to discuss it offline during this week. Why do I think it's relevant? Well, because to understand this object here, you have to understand what happens to scattering amplitudes in infrared limits, so let's say in the soft limits, but beyond leading power. Okay. Again, I will not have time to discuss it today, but this is something that we don't understand very well and may have important consequences. So what I will do right now, I will just ignore all of these subtleties. I will ignore that this picture may have massive corrections. I will ignore that there may be issues here, and I will just assume that this formula is correct, and then someone will tell me what these objects are. As I said, these objects describe the probability of finding a quark or a gluon inside the proton. We cannot predict them right now, so someone will measure them, and people measure them at a 3D because it's a good precision. So this we can have a few % precision is possible, and it's improving by the day. And then our task is to get the partonic part, so this bit here, as precise as you can. Okay, and here is where scattering amplitudes are, of course, because when you start computing observables, you use perturbation theory because this happens at a high scale. So this object here, let's say for this object, we'll have a leading order contribution, and then you expand. And the more you get, the more precise you are. And of course, this object here contains relative correction to this object here. So if this is this will contain one loop scattering amplitudes. This will contain two loop scattering amplitudes plus other stuff, and so on and so forth. Okay. So here is where the scattering amplitude part of the game enters. Okay. Now, this series, as you probably know, are not convergent, but we don't care because the asymptotic behavior kicks in at much higher order than what you can even think of computing right now. So for us, this would be a perfectly good series. We're very far from the asymptotic behavior. There is something annoying about this series, and this is the first thing that we don't understand about this game. What is annoying is that we expect this coefficient to be parametric for the 1. This is a nice expansion, but they're not. So we found very large corrections. And this we don't understand. So that's the first question mark. And maybe understanding better the structure of scattering amplitudes would allow us to understand better what structures are universal and what structures are not universal, and understand better why these corrections are large. Just to give you an idea, so if I do this, if I compute the Higgs, which is one of the most interesting processes we can compute, the first correction is as big as the leading order. And the second correction is basically 50%. So the series is almost not converging. And then you have to go to higher and higher and higher order to get something which is decent, okay? Which is a problem. And this doesn't happen, for example, in the plus-minus annihilation. This seems to be a feature of hadronic collisions. It doesn't happen in deep inelastic to some extent. So this is something we don't understand. So there is something, some structure to be seen. And it may very well be that we are defining these objects in an optimal way. And if we will actually be able to, as I said, understand some universal structure in the scattering amplitude part of this, we can basically recollect them somehow and improve this picture. But so far, this is all wishful thinking. We don't know. Now, the problem here is that if we want to compute this, we cannot change the theory. Okay? So if we don't like the fact that QCD is horrible, too bad for us. Okay? So we really have to compute scattering amplitudes in QCD or in more in general standard model. And this makes life much, much, much harder than in other theories, to the point that we don't know much about scattering amplitudes here. So you may be surprised to hear this, but the best that so absolute state of the art for QCD calculations is 222 at 3 loop and 223 at 2 loop. Okay, so we cannot do better than this. Now, I'm sure that many of you, as I said, will be very surprised. In other theories, you can do much better than this. But what I will try to explain in these lectures is at least in part, why this is so complicated and what are the obstacles that are preventing us from going further. Okay. Now, there are some obvious differences between QCD and nice theories, let's say. So, of course, we are not dual superconformal. So we lose a lot of symmetries. And one of the immediate consequences of this is that we have a bad UV behavior. So this makes the structural scattering amplitude much, much, much more convoluted. And in a way that even the organizing principle that we know and love for n equal 4 are actually misleading in QCD. Sample QCD is not UT, not universal transcendental. It's typically not pure. For scattering amplitude, the principle of maximum transcendentality that you may be familiar with, so the fact that the maximum transcendental part of QCD is equal to n equal 4 doesn't work anymore. And you say, well, can you try to rescue somehow? Well, the answer is no, you should not, because, for example, if you insist in writing down the QCD amplitudes in terms of pure and UT functions, you completely obscures its behavior. And you get something that doesn't show the actual structure of the theory. And this is basically related to the ultraviolet. So the ultraviolet screws you a little bit your theory and make in such a way that it's no longer that these are no longer good guiding principles to some extent. Okay. So I thought that there was a talk last week by David Kostover that he touched upon this. I will briefly touch later on. Now, this is one thing. Now, there is another thing, on the other hand, that works in QCD, which is large n. Okay. So this doesn't matter if I have or don't have supersymmetry. So large n, planar limit, everybody's happy. However, at the end, we're not interested just in QCD, but we're interested also in standard model. And this immediately destroys this as well, because just imagine you have a beautiful planar two-loop amplitudes for scattering some gluons. And now you want to produce a Higgs. But the Higgs is not colored, so you can attach it to wherever. So you can attach it here and makes a beautiful planar integral immediately non-planar. So in pure QCD, we have large n, it's actually very good. But in reality, many of the processes that we were interested in, we cannot use large n. There's another subtlety, and again, this is mostly an introduction, but there are some also regions where large n is not a good approximation. So we know that in general, large n is beautiful, right? Because that's all the argument from Witten, right? So it's perfect approximation. You expand in over c squared. Unfortunately, there are situations in QCD, typically when you have forward scattering, where sure, you expand in over c squared, but the coefficient turns out to be I pi squared. And pi over 3 is not a small number. Okay? So typically, this happens for forward scattering. And you may say, well, why do we care about forward scattering? Well, a very nice forward scattering process is Higgs production in vector boson fusion. So I have one jet that goes in one direction, one doesn't go the other direction. This allows to select vector bosons in the T channel and allows experimentalists to study the structure of the Higgs coupling. So these are plagued by this objective. OK. So that's more or less the situation right now. So what can we do then in QCD? Well, what we can do in QCD is that, as I said, it's not particularly exciting. So we can do tree-level. I'm pretty sure you're not impressed by this. Yeah. Sorry, repeat the question, yes. So what is the state of the art for QCD amplitudes? So pure QCD, so everything is massless, so parton scattering. We know 2 to 3 at 2 loops, full, leading color, subleading color, everything. And at 3 loop, we know 2 to 2. Okay? So this is pure QCD. Full amplitude, subleading color, everything. And in case of 2 to 3, of 2 to 2, as you can imagine, kinematics is very simple. So getting there is a nightmare, but the final result is simple in some terms. While 2 to 3, it still looks horrible because we don't have a good way of simplifying the kinematics. If you start having not pure QCD, but something like Z boson, whatever, then we have planar, 2 to 3. We have the integrals for the non-planar, but not the amplitude, not the full amplitude yet. And very recently, people computed the integrals for 2 to 3 with 2 masses, let's say WW. Okay? So that's the status right now. The second you start having top, let's say, some masses inside, you get elliptic stuff, and you're done, basically. So we have only partial results in those limits. Now, people are very pragmatic. So in many cases, they say, fine, I don't care. I just pure QCD. Yeah, pure QCD, that's it. Now, everything. So gluon, quarks, photons, whatever, everything which is massless. Now, there are people in the audience actually working on, let's say, Z plus jet. Okay, so 2 to 2 with 1 mass. And they have some partial results. And I don't know, I don't see people. Maybe you can say what you have, right? So. So getting close to get leading color Higgs plus jet. No. Higgs plus jet. So 2, 2, 2, but with one mass. So with one off-shell leg. Okay.
Yeah. So the leading color for the Z is done because it's planar. Z plus jet. X plus jet is non-planar in leading color, and we are going in that direction. But it's much more difficult than the Z plus jet. Both the integral and the reduction is much more difficult.
Can you say what's known about like just pure electroweak stuff, even like precision electroweak beyond one loop?
Vertices are known. So basically every 3-point function is known numerically. Okay.
Known at
next to next leading order. So at
two loops.
Then the whole renormalization procedure is known, which is non-trivial because you have all these complex poles and all this stuff that you have to be careful about. Now, what happened more recently is mixed QCD electroweak. Okay, so for this, you know, full 2-2-2 at 2 loops. Okay, but in many cases, you know it only semi-analytically. So part of it is numerical. So there are some simple cases. Let's say when you neglect the mass of the leptons, which is very good approximation, and you neglect all contribution from top and bottom. Then you have some analytic formulas. These have been remapped in terms of actually standard classical polylogs with weird arguments. And this is what is known. So beyond
so if someone
that,
handed you a Z factory tomorrow with 10 to the 12 Zs, you'd have a lot of work to do to get to a part in a million on Z couplings.
Yes. But yes, but people are working on it. And I would say very pragmatically. So there's really, so in this game, a lot of people try to understand structure. A lot of people say, look, we need to just get results. So let's put them on a computer, let it run till it dies. In my case, it would be very great to have a Z factory tomorrow, but it will not happen tomorrow, right? So it still makes a little bit of sense to try to understand structures before just wasting computing power right now. But that's my hope. Okay. But yes, plenty of work to do. Very good. So 3 we know, 1 loop we know quite well, and then there's a barrier. So in QCD, the problem happens when you jump between 1 loop and higher. Okay? And to me, this is a conceptual barrier. Then going from 2 loop to 3 loop, of course, is much more complicated. But the point is that we use different techniques to go from here to here. And here, technique scales very, very badly with the number of legs and the number of loops. So that's the problem. So why this happens? Well, because the trick that we use here, we don't know how to use them here and here. So what we do here, we use quite brute force approaches that work, so we can get results, as I told you, but they are not optimal. And there's a huge amount of work of possible improvement that one can do in this sector, basically on all possible aspects of scattering amplitude. So get a good integrand, get a good set of integrals, get some numerical stuff to evaluate that. Because here, at some point, when we want to use them for QCD predictions, we want to get numbers out of this. Okay. So if you give me the symbol of the amplitude, I'm very happy, but it's not enough. Okay. So at the end, we need to put them in a computer and evaluate them fast. Now, what I will try to do today is basically going through quickly why 1 loop is so nice and what are the problems so what are the techniques that we can use there and why we cannot use them easily at 2 and 3 loops with the hope that maybe some of you will get some ideas. Okay. Now, in 2 words, we know how to do 1 loop because of 2 things. One, we have extreme control on the structure of the amplitudes, of the integrand, sorry, because it's very simple. So we can put on a computer and let the computer do the hard work. 2, unitarity works extremely well at 1 loop because the number of unitarity cuts are small. So with a bunch of cuts, we can get mostly everything. It's not the case at higher loops. And 3, the basis of functions where 1 loop amplitudes live in QCD in any theory is very, very simple. This was proved by Eric Pantz and friends long time ago, Francis Brown, sorry, and a long time ago, that these are basically generalized polylogs, no matter how complicated your amplitude is, no matter how crazy you go in your status. Okay, so basically simple integrand, simple unitarity cuts, easy to put on a computer, and simple structure. Now, why it is so easy? Let's try to use this thing now. And because basically, any one loop amplitude can be written in terms of extremely simple building blocks. This we don't need them anymore. So it turns out that if you have a complicated one loop amplitude, let me write it this way. So I have a loop momentum, then P1, P2, P3, and endpoints. Okay, so here we'll go L plus P1 that I call Q1. This is just to set notation. L plus Q2, which will be P1 plus P2. L plus Q3, It turns out that no matter how complicated this object here is, it can always be written at the integrand level with a small caveat as a sum of coefficients that depends on the process. So if the example of QCD or something else, times some box coefficient plus something with triangle coefficients, something with bubble coefficients, plus if you have internal masses, something with tadpoles, plus something else that we'll explain in a second. Now, these are boxes, triangles, and bubbles, whatever, scalar integrals, okay, so no numerators, just pure scalar integrals that can be obtained in all possible way of pinching these diagrams, okay? Now, as you can imagine, this is not entirely trivial because I have an endpoint function amplitude. I would imagine maybe to have n-point integrals, but at one loop it's not the case. You can have at most 4-point integrals, but this relies crucially in the fact that you want to be close to d equal 4. What do I mean close to d equal 4? Well, it means that the loop momentum, there's nothing I can do, so the loop momenta will develop singularities. So since it develops singularities, I will have to regulate it somehow. And here we don't have supersymmetry, we don't have conformal invariance. So for us, dimensional regularization works super well. So we just use dimensional regularization. So we go a little bit away from d equal 4, but we do not allow external degrees of freedom, so polarization and momenta of external particles, to go in d dimension. Yes?
Third regularization scheme, or can you use other regularization schemes like cutoff or econ or something?
So you understand correct. So the question is, do we have to use dimreg or can we use something else? Yeah. In principle, you can use what you want, but there's a humongous advantage of dimreg. So it doesn't destroy any of the symmetry of your theory. So you see, we don't have problems that you have in n equal 4. And it doesn't introduce scales. So that's why dimreg is so important. So it doesn't introduce scales, so it makes the integral simple. So if I use something that puts a cutoff or internal masses or whatever, makes the calculation prohibitively difficult. So we cannot do anything at that point. Just in principle, you can, but technically it becomes too complicated. So this is the practical answer to your question. There is also a more subtle conceptual part of your question. So dimreg has a unique feature that puts all scaleless integrals to 0. Okay? So if you have an integral which doesn't have scales, dimreg puts it to 0, and what it does internally is that it cancels a UV singularity against an infrared one. So what dimreg does is that it splits around, it moves around UV and infrared singularities, and in many cases it's a disaster, an absolute disaster. So this is part of why we cannot do this. Okay? So because we use a trick that shuffles around the wrong kind of singularity. But there are cases in which this property is extremely useful. And if we have time, we'll see one example tomorrow. Basically, you have integrals that you want to expand in some particular regions. Okay? Just imagine that you have an integral that has a complicated integrand function. But this becomes very simple if the loop momentum is small. Okay, so what you would like to do, you would like to integrate between some infrared cutoff, so we can do this expansion and then do something like that, okay? And there are cases, as I said, if we have time, we will do it tomorrow. So where this becomes simple because you can do one kind of expansions, this becomes simple, we can do another kind of expansion, okay? So that's just a fact of life. So you have a function that can be expanded into limits. The amazing property of DIMREG is that it turns out that you can extend the integration region to all space, making this much more symmetric. And the reason, again, so if we have time, we'll see tomorrow, is that the error that we are going to make with double counting produces scaleless integral, which has 0 in DIMREG. So this makes the construction of effective theories very, very simple in DIMREG. Okay? So this is the condition under which this is true, okay? And this is also a reason why it's not so easy to do Z2 loops, because, okay, sorry, I forgot to say something. So an important part of this representation is that this object here, all of them, depends on kinematics, but do not depend on the dimension anymore. Okay, all that depends on the dimension is hidden into these transcendental objects. Okay, but crucially, this is true only close to 4 dimensions. Okay, now this makes your calculation much simpler. Okay, so if you're allowed to be close to 4 dimension, you don't need to care about these objects that are absolutely horrible and completely non-physical. Okay. Unfortunately, when you start going to 2 loops, you have contributions that look like 1 loop squared, and 1 loop is singular. So you can no longer do this. You need to have this. So right now, we do not know how to immediately extract the physical information from, let's say, 2 loop amplitudes in a way that doesn't clutter them with spurious unphysical behavior. Okay? And there are people here, our organizers are working to try to understand this problem better. So basically, this is a huge problem because you know that every time you force QFT to do something stupid, you get an idiotic result. Okay? And here is a typical example. So we insist in having intermediate results, which beyond 1 loop require this part here, which is completely unphysical. And the price we pay is that we get absolutely horrible intermediate expression that only at the very end simplify. But they may be so complicated that even if you get the result, it's too difficult to simplify. Okay, so, but what happens at 1 loop? So at 1 loop, this works. And as I said, it's not entirely trivial, but the point is the following. Imagine that you have first a tensor integral, okay, with more than, which is higher than 4 point, okay? So let's say n point with n greater than 4, okay? Then this comes automatically with more than 4 external momenta, okay? So you can use this momenta to parameterize the component of your 4-dimensional loop space. So if you write your loop momentum as sum of alpha I qi, if you have more than 4 of this object, this is a complete. You can always find define change of variable such a way that this object here completely span the physical space. And then what you'll have something that lives in the space which is not spanned by these external momenta, which is forced by assumption, basically, to live in epsilon dimensional space, so that L dot epsilon is 0. Now, this is a completely valid parameter. Yes? Qi, for me, all the external particles right now are on shell, so they're all 0. Okay? But Qi will not be on shell because you see, for example, Q2 is P1 plus P2, so Q2 squared will be S12. Okay? Does it answer the question? So this is a possible way of parameterizing momenta. There is a cute trick that I want to show you, because if you understand this trick, basically you can do one loop calculations without even thinking. And the trick is to use a slightly different basis, which makes the determination of these coefficients here straightforward. Okay? So let me define a vector, let's say v1, which is the following. Basically, I will define this symbol in a second, okay? So what is this object here? Well, this object here, delta mu1, mu n, mu1, mu n, is a contraction of two Levi-Civitas. Okay? So this is epsilon mu1, mu n, epsilon mu1, mu n. So that's a completely antisymmetric object. And in particular, this object here, dotted into any momenta which is not Q1, gets to 0. Okay? So this basically defines a space which is orthogonal to all loop momenta but one. Okay? And this is just a normalization factor. So this delta 4 is just a normalization factor. So what happens if you put Q1 here? Well, this you know, if I do something like that, Q1, Q4, Q1, Q4, that's just a Gram determinant. This is just that Qi. Sometimes you find this as Gram Qi, Qj. Okay. Now, why is it useful to define these vectors? I can define one for 1, 2, 3, and 4. Well, because I can use this to span the loop momentum space in a way that makes the composition very, very simple, because then I can write a loop momentum as the sum of alpha I vi. So with I goes from 1 to 4. So this gives us a basis for the physical space, plus this epsilon component. But now, if I contract L with Q, now Q lives in 4 dimensions. So every time I do L epsilon dot Q, this is 0. Every time I say, let's say, Q1 dot L, V2, V3, and V4 will be 0. So this immediately tells you that the coefficient of this object is L dot Q. So basically, this is a very nice way to expanding loop momenta in an object, which is very nice because you recognize that this is a difference of two propagators. Okay. So since this is a difference of two propagators, whenever you have a tensor integral in dimension higher than 4, you can use this object here to reduce it down. Okay. So let me be more precise. Just imagine that I have a one loop amplitude with some loop momentum. Well, I will always use that dl is the usual dl over 2 pi to the d. Okay. And then some complicated tensor integral, L mu ta ta ta, divided by your d0, d1, dn, contrasted with external objects. Okay. So generic external object, let me call it u. So u I with mu, also u1 mu, u2 nu, ta ta ta. Well, this can be basically momenta, polarization, whatever you need to construct your amplitudes. But the important part is that by assumption, these are in 4 dimensions. So whenever you do something like that, this object here disappears. And that object can be written in terms of, so the general structure that you have here is u I vj, this is non-zero, okay, times structure of the form L dot qi, which, as I said, is basically L plus qi squared minus L squared minus qi squared divided by 2. Okay, that's basically difference of propagators or objects with lower rank. Okay, So in this trick, without even thinking, you can take a rank 72 million integral and systematically go down, 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 and getting an integral which has less legs or less numerators. Okay? So this tells you that every time you have enough momenta to write this decomposition, so more than 4 external legs, you can do this and go down completely by rank. So the only thing you need to discuss is what happens if you have a scalar integrals with more than 4 propagators. Okay. And what happens is that there's a small subtlety because it depends a little bit on whether you have. Sorry? Yes, you will have to keep reminding me, okay? So, oops. Yeah.
In this space, you have the dimensions of your space that depends on this parameter epsilon, which is a real parameter. Okay.
Yes.
Let's say, how do you define, let's say, an Hilbert space on a real dimension?
What do you mean Hilbert space? You see, right now I'm just doing kindergarten linear algebra. I'm not doing anything fancy. Okay, literally. So why do you want a Hilbert space?
I mean, so if you want to define, let's say, the contraction of two vectors, okay.
I define it like this. Okay. What this is? Sorry, I may see what your point is. You see, this I only use it with the 4-dimensional part of it. Okay.
Okay.
So is this what you are after?
Yes, because I mean in principle, if the dimensions of this epsilon subspace is epsilon, you should need like I don't know, maybe epsilon vectors to span these bases, but epsilon is a real number. So I don't know how it is defined.
Yeah. Now here we don't need this because basically here we do everything in 4 dimension. But remember how dimensional regulation works. So nobody tells you that you do integrals in 3.5 dimensions. So people tell you that you do integral in 3, 4, 5, 6, 7, and what comes out is the result can be analytically continued in the dimension. So you have to think it as I always live in fixed number of integer dimension, and then the result is a nice function I can analytically continue. And complex analysis is a unique way of doing it, so you don't run into troubles. Okay.
Okay.
So that's the gist. If delta 4 vanishes, that's an excellent question. So you cannot use this trick, okay? So, but if delta 4 vanishes, you are in the general subspace, okay? And basically what you can do, you can play tricks. And if this happens, basically you have some coplanarity, and you can define something extra orthogonal to this space and play. So this is an excellent question. So here I'm assuming that I'm in generic kinematics. If I'm not in generic kinematics, all these formulas don't work and becomes technically more involved, but the point is you know what to do. So it's slightly more involved. I can show you how to do it later on if you want. But that's very good. So we assume that everything is non-special kinematics. Okay, so what happens if we have now scalar integrals? Okay. So as I said, everything which has a numerator can be reduced down, so we need to only consider scalar integrals. And let me consider 2 cases. So n equal 5 is special. Well, n greater than 5 is easier. Okay. So let me start from n greater than 5, and for definiteness, let me put n equals 6. If you see what I'm going to do, it's clear that this doesn't depend on the number of these objects. Now, what is our loop momenta? Well, our loop momenta is sum of this alpha I and this nice vectors here plus an epsilon. So this is basically 5 degrees of freedom. So 4 from this and 1 for the auxiliary space. Okay. So if I have, sorry? sorry, that's the number of denominators. So that's a 6-point function. Yeah, if you want. So I have 1, 3, 4. So 1, 2, 3, 4, 5, 6. Okay, you can have millions, but the point is that it's an integral that has 6 internal. But it's an n-point function. Okay, so we have something like that. Okay. Now, if I have 6 or more propagators and I live in a space which has at most 5 degrees of freedom, I must have some relation between them. In particular, now we have to go back a second to this. Okay. So you see I have Q1, Q2, Q3, so Qn doesn't exist. Okay. So just imagine I have a bubble. So this is L and this is L plus Q1. So when we consider all the Qn's, they go from Q1 to Qn minus 1. So the statement that all these momenta, which are more than 5, are independent, is equivalent to the statement that this equation has solution, has a non-trivial solution. The solution with alpha I different from 0. Okay? Then I can define alpha n as 1 minus their sum. Okay? And I can write we don't need any more. I can write the following. Alpha I di, when these are the denominators, is sum. Alpha I, what is di? Well, it's L squared plus 2 L dot Qi plus Qi squared. And then if you want, put a mass, don't put a mass as you wish, okay? But you see that the sum, so this object here is 0, okay, by assumption, because I defined the last one as 1 minus all the other ones. And this object here is 0 because this cannot be linearly independent. Okay? So you find a very nice relation, alpha I di divided sum over I alpha I Qi squared minus mi squared is equal to 1. So you have your 6-point function, you multiply by 1, and this removes it down and deletes propagators, and you can systematically do this and go from an n-point function to a 5-point function. Okay. Then the last part that we need to do to prove that formula is what happens with the 5-point function. What happens with the 5-point function is slightly more subtle, because I have this object here. So it's true that here I have only 4 degrees of freedom, but I also have the extra degrees of freedom. Okay. So what can I do? Well, what happens is that in n equal 5, I have an extra relation okay. So L squared, which is my first denominator, plus m squared, what is it? Well, if I use the definition of L as sum over L dot Qi Vi plus L epsilon, I can write it as L dot n epsilon, just to use the same notation. The epsilon is a normalized object, at least in the extra dimension. Okay. So if I take L squared, okay, I get that this object here gives rise to basically either denominators or objects don't depend on loop momentum, so L squared is equal from here. I get terms that contains denominators, terms that don't have loop momentum anymore, so basically q square minus m square, stuff like that. And then we get this extra term here, L dot n epsilon squared. Okay. So again, I can play similar game as before. I can say that then this object here, L dot n epsilon squared, is equal to denominators constant. Okay, so I just bring this here. It's something like that. So something that doesn't depend on the loop momenta. It can only depend on loop momenta through the denominators. So if I have denominators, that's fine. So I can just, every time I have denominator, I'm reducing down, so I don't need to care about it. So what I have to care about is this part here. And this basically tells you that I can define one, in this case, as L dot epsilon squared divided some constant. Okay, that's a different one with respect to before. And now, what happens if I plug this one in my, sorry, not dot epsilon, n epsilon. What happens if I plug this one into my integral? So I get my integral okay. So this object here must live in the extra dimension. Okay, so we said by definition the projection extra dimension. So this object here gives rise to something that vanishes in 4 dimensions. Okay, so naively you can. So little n is just I define a vector which spans the extra, which lives in the extra dimension. Okay, and I just define such a way it's normalized and it's orthogonal to everything else. So I can just write this in the same notation as everything else. It's just a rewriting. There's nothing subtle there. So you maybe tend to say, great, that fixes everything because through this one I can reduce down to the price of having something which is proportional to epsilon. I can remove in 4 dimensions, but not so fast because this could have divergences. Okay, so you have a numerator, but you have to be careful of what happens if the integral itself develops divergences. Okay. And I just want to show you this example because it turns out that this is actually a very nice object. And it does not have divergences. Now to see it, let me define an extra vector. Okay, so similar to the V, remember the V were defined, let's say V1 was defined as delta mu Q2, Qn, Q1, Q4, sorry, not n, divided the gram determinant of this 4 object. Now I define something similar, but with one extra component. So basically, like it was a 5th-dimensional object. So I put here also the loop momenta. Okay, divided by some normalization that we will fix in a second. Okay, now it is obvious that this is the only one we'll define, so I move the 1. That, as before, if I dot it with Q, this is 0. Simple exercise to see that if I dot it with the previous ones, it's always 0. Okay, so this is also orthogonal. Okay, what happens if I dot it with L? Well, if I dotted this with L, this becomes the gram determinant of the 5-point system. So basically, Q1, Q4, QL. Okay, so this becomes a gram determinant of 1, 2, 3, 4 L. I call this delta phi. Okay, with N. And then if I choose, so I can, this I'm defining, so I can choose whatever I like. I choose n equals delta 5. Okay, such a way I can make this one. Okay. Now it's a simple exercise that the last thing that you need to know is what is omega with itself. And this is a simple exercise. What you get is that this is delta 4, delta 5 divided this normalization squared. So if the normalization is delta 5, this is delta 4 over delta 5. Okay? So why have I defined that object here? Well, because that object here basically gives me an explicit representation of what you just asked. So what is an epsilon? So basically, I just constructed an epsilon. Because this clearly lives in the extra dimension, so I can use it like an epsilon, and I will have that in general, my loop momentum will be alpha I vi in 4 plus some coefficient I don't know times this w. But again, so if I just now dotted in, okay, so I know that v dot l, so 1 is v dot l, which is equal to 0 plus c v squared, which is delta 4 over delta 5. So this tells me what this object here is. Okay. So this is just okay. And then because of this, if I now consider the integral that I was scared about, the one that could develop divergences, okay, so this object here is, I just plug in this representation, and the integral of, what was that, L epsilon squared over d0, d5 is just delta 4, delta 5 omega square, which is the integral. So delta 4 goes downstairs, and then the integral of delta 5, d1, d2, d3, d4, and d0. Okay? So this is this Gauss determinant that lives in 5 dimensions. So clearly this is order epsilon. Okay, so it's the same as before, but it says something much more. So since this is constructed in this way, so every time L becomes soft, that object is 0. Every time L becomes collinear, so basically proportional to another momentum, that object is 0. So this destroys all, automatically destroys all possible infrared singularities that this integral can develop. Now this, by power counting, cannot have anything in ultraviolet, so this is finite, and we can cancel that. Now, this trick of defining these Gauss determinants to get something finite is actually generic. So I just show you the simplest possible example. But people are actually playing, I showed it to you because people are playing with this at 2 loop, and they're trying to get something similar to make sure that they get the basis, which is written in terms of very nice finite object. Time to start, time to pause.
Maybe there's time for some final questions. Oh yeah, actually, yeah.
Just a quick question. You said that the 2 to 3 like state of the art for QCD, it was all massless external legs.
One massive.
Oh, one massive. Okay, what is the obstruction to having? This is a stupid question, but what's the obstruction in your formalism? It seems like you could have external masses. It's fine. What's the obstruction to having 5 external masses in state of the art calculations at the same loop order?
Well, you see here, if I have masses, not massive, nothing changes because I have one loop. Okay.
Right.
So the situation just becomes. I mean, formulas become more cumbersome, but that's the beauty of one loop. So everything becomes more ugly, but nothing changes. While at 2 loops, I will show you later on, we cannot use these tricks. So these tricks fail, and then just becomes too complicated. So having 3 masses, we cannot do it, not because conceptually we cannot do it, but because it's too complicated. So practically, you put it, even if you use a computer, it just doesn't do it.
Okay, just the integrals are
It's not even a question of integrals. It's a question of getting a representation of the integrand is already bad.
Okay.
And then the integrals also are terrible, of course. But
Can you repeat what you mentioned about what happens when you decorate the external lines of these integrals with more than 4 edges? Because I think you mentioned something about what happens when you put helicity or vectors and they're
yes,
not
you
just
see,
scalars.
for me, this object here, you see, right now I'm being very, very stupid. I'm using just Feynman diagrams if you want, right? So my object will be of the form, my tensor integral L mu, L nu, L whatever, okay, over all my denominators. And then this will be multiplied by polarizations, momenta, whatever you like, okay? So the trick of this decomposition is that since I write L as sum over L dot Vi plus L epsilon, okay? So every time I contract this with this, I get 0 because it's a 4-dimensional. Every time I contract this with this, I get something, but I don't care because all the structure that I need to care about is here. Of course, if I want the final result, I need to keep track of all these things, what it is. But structure is completely irrelevant. I have external polarization. I don't have them. This is a scalar theory, not scalar, completely irrelevant. Okay, the structure is the same. This is the power of one loop.
Thank you so much.
Mm-hmm.
Can you repeat the question?
Yes, so the question is, if you remember, I said, okay, this object here, this L epsilon here, gives rise to something which is order epsilon. So I can throw it away unless this hits a 1 over epsilon pole that comes from some configuration. Now, these are integral which has 5 denominators and nothing upstairs. Upstairs only in epsilon dimension. So this cannot be ultraviolet, can only be infrared. Okay, the question is, how can I get 3 for infrared? Well, I wrote down that this object here, okay, can be rewritten in terms of this 5-dimensional gram integral for gram determinant. And this gram determinant it was written somewhere, okay, but okay, if not, I can just rewrite it. It's basically, oh, it's this here, this object here, okay? So where can I get infrared singularities? Well, I can get infrared singularities whenever L goes to 0, but this is linear in L, so this will kill the infrared singularity, the soft singularity. Okay, so this can be at most logarithmic, so this will completely destroy it. Or I can have collinear regions when something goes on the light cone. Okay, but if it's collinear, so this can be written as a linear combination of external momenta, so a linear combination of Q. Since this is you see completely symmetric in all the Q's, it will go to 0. So the trick is that if you use this parameterization, this makes it immediately obvious that this object here is not just order epsilon, but it's also the numerator vanishes in any possibly dangerous infrared configuration. And actually, for people who know what I'm talking about, that thing here is the pentagon in 6 dimensions. Okay, so that thing basically uplifts everything 1 dimension higher where there are no singularities.
So at one loop, you started by saying that if you had 1 million particles, it doesn't matter. You still have an expansion in boxes, triangles, bubbles, et cetera. And what you described is an explicit algebraic way of reducing anything. But there's also this sort of quick, sort of conceptual way of seeing why it had to be true, because you have in 4 dimensions, 4 loop momenta. You can't cut more than 4 things, so you can't have anything more than a box. Yeah. Is the analog of that argument at 2 loops sort of fully understood?
I don't think so. Maybe other people in the audience understand it better than me. But to me, I was going through this because then I will try to make connection with exactly what you said and say, look, there's a fast way of doing all of this. And as far as I understand it, at least the same doesn't really work well at 2 loops. That's one of the big problems. Because if we knew something similar, okay, and something similar that also allows us to go all the way down, okay? Because, okay, maximal cut, fine, we understand it. But the question is, can we cascade down? And to me, maybe technically you can, but you don't see the beauty and the simplicity that you see here. And maybe it's a fact of life, but maybe we don't understand something. But I mean, people in the audience.
But just experimentally, for example, is it true that all the integrals at 2 loops are basically, I don't know, pentaboxes at most, something with 8 propagators and then down?
You have, there are actually some there are some restrictions on which kind of integrals you can have, and this just comes by counting. So basically, you count all possible things that you have, And then you find that for any loop order, you can have at most some set of propagators, because then the rest. So there is some limit, and it's really counting access. I don't remember what the limit is, but there is a limit.
Thank you.
All right, so no further questions, and Fabrizio will continue at 10:45.